Hello students, now I am going to start the very important topic in the conduction chapter called as the critical radius of insulation. Actually, when you think about the insulation, when you talk about the insulation, why do we insulate anything? Why do we insulate a body? Generally, our prime idea in the main idea in the mind is, yes, I want to reduce the heat transfer rate. I would like to pack up some insulation around the body. Say for example, our human body is feeling so much of chillness in the peak winter. Definitely, you will take the sweater and wear it. What for? To make feel warmth. That is to reduce the heat transfer rate between the body and the air. Definitely, you would like to wear the sweater. That is a general idea, general perception regarding the heat transfer and the insulation is putting the insulation, definitely it would result in the reduction in heat transfer rate. That is our general perception, but that is not true all the time. That is not true all the time. There are few cases where you are going to see that after putting the insulation, you are going to observe that heat transfer rate will increase. Instead of decreasing, heat transfer rate from the body to the surroundings, it will increase. Why does it happen? When does it happen? That is the main concept regarding this critical radius of insulation. Very important topic because many times the questions were asked in the earlier gate examination regarding this particular topic. Let me discuss, let me discuss about the critical radius of insulation. This is the main concept. Generally, for sufficiently thin wires, for small radius wires, maybe few mm, maybe 2 mm or 3 mm or maybe around 1 centimeter like that. For small radius wires or even pipes, for small radius pipes or wires, putting the insulation around the wire or the pipe may result in increase of heat transfer rate as compared to the case where there was no insulation around the wire. Supposing it is like this. This wire, I have taken a small wire, radius is maybe around 5 mm or 6 mm. It is a bare wire, there is no insulation now there. There is some, it is a hot wire, bare wire, no insulation, but radius is relatively small. There is some heat transfer happening from this bare wire to the surrounding atmospheric air. Now I wrapped a little bit of insulation around that wire, little bit of insulation I have packed it, okay, around that bare wire. Now you will be surprised, you will be really astonished or surprised to see that after putting the insulation around that wire, heat transfer rate would be more as compared to the case where there was no insulation. As compared to the bare wire, after putting the insulation, you will be surprised to see that heat transfer rate is becoming more. Why it is happening like that? That is the main concept of this critical radius. I would like to derive the equation for the critical radius. First, I have considered a bare wire, a solid wire of radius Ri. A solid wire of radius Ri I have considered. This is the axis. A solid wire. Around that wire, I have wrapped the insulation. Around that solid wire, I have wrapped the insulation having a thermal conductivity K. K is the conductivity of the insulation. RO is the radius measured up to the surface of the insulation. L is the length of the wire. K is the thermal conductivity of the insulation. Outside ambient air at T infinity. Inside this solid wire, I am passing some electric current. I am passing and generating the heat. Whenever you pass an electric current inside a wire, heat will be generated. I have considered a solid wire inside which heat is being generated by passing some electric current. Around that wire, I have wrapped some insulation whose conductivity is K. and after wrapping the insulation, the radius measured up to the surface of the insulation is RO. There is ambient air at T infinity. So, because of this passage of electric current, there is a heat generated inside this solid wire, right? So, that heat generated inside this solid wire is radially conducted through the insulation, and from the surface of the insulation, that heat is convected to the convection to air with a convection heat transfer coefficient of H. Okay. The heat generated inside the wire is radially conducted through the insulation, and then from the surface of the insulation, heat is convected to the ambient air with a convection heat transfer coefficient of H. Consider a solid wire. I am just describing that. I am writing this here, what the situation is. Consider a solid wire of radius Ri, inside which heat is being generated by passing electric current. Let an insulation having a thermal conductivity K let an insulation having a thermal conductivity K is being wrapped around the wire up to the radius RO. Is being wrapped around the wire up to the radius RO. Okay. The heat generated inside the wire due to passage of the current, is radially conducted through the insulation and then from the surface of the wire heat is being convected and then from the surface of the air heat is being convected to ambient air with a convection heat transfer coefficient of H. H. watt per meter square Kelvin. The heat generated inside the wire is radially conducted through the insulation, and then from the surface of the wire heat is convected to the ambient air. What is the temperature of the ambient air? At T infinity, ambient air temperature at T infinity with a convection coefficient of H watt per meter square Kelvin. So that is the situation. Assume steady state heat transfer conditions. Assume steady state heat transfer conditions between wire and ambient. Assume steady state heat transfer conditions between wire and ambient. So this is the direction of the heat flow. You can notice this. This is the direction of the heat flow. Let T, supposing under steady state heat transfer conditions, let Ti be the surface temperature of the wire. Let Ti be the surface temperature of the wire. Under steady state. Let Ti be the surface temperature of wire under steady state. Now between the Ti and the T infinity, if against this radial heat transfer between the wire and the ambient air, there is a heat transfer taking place. How many modes of heat transfer are there between Ti and T infinity? There are two modes. One is conduction through the insulation, and there is a convection between the surface of the insulation and the air. If you just look at this figure, Ti is the temperature of the wire, right? There is a radial heat transfer happening between the wire and the ambient. So how many thermal resistances you may expect between the wire and the ambient air? One is conduction here, look at this. One is conduction here, and then followed by the convection between the wire and the ambient. First conduction, radial, it is a radial heat transfer only. First conduction here, and then from the surface of the insulation to the air by convection. So there are two resistances you may expect for the radial heat transfer between the wire and the ambient. So drawing the thermal circuit for radial heat transfer, between wire and ambient. Drawing the thermal circuit, there are two thermal resistances you may expect. One is Ti. First resistance will be conduction. Of conduction resistance offered by what? Conduction resistance offered by the insulation. First resistance is conduction. And then we have the convection resistance. What is the first conduction resistance? Ln Rho by Ri divided by 2 pi KL. Okay, the first resistance will be the conduction resistance offered by the insulation. K is the thermal conductivity of the insulation, not the wire. Okay. Between Ti and T infinity, I am talking about this radial heat transfer. That is, one resistance is offered by the insulation, that is given by conduction resistance, ln rho by ri, look at this, ln rho by ra divided by 2 pi kl. And then we have the convection resistance at the surface of the insulation. That will be 1 upon HA. What is the area of convection at the outside surface? 2 pi ROL. Area of convection is always the area of contact between the body and the fluid. If you just look at this, what is the area of contact between the insulation and the air? 2 pi RO perimeter into length here at the outside surface. So, we have the two resistances in series. The flowing current is Q. Therefore, rate of radial heat transfer between wire and ambient Q is equal to Ti minus T infinity divided by sum of the two resistances plus 1 upon the convection resistance 2 pi ROL. Okay. So, if you just look at that equation carefully, if you just look at this equation, there are many parameters that remain constant. There are many parameters that remain constant in this equation. L is the length of the wire, constant. K is the thermal conductivity of the insulation, constant. Ri is the radius of the wire, that is also a constant. L is constant. K is the property of the material of the insulation, constant. Ri is the radius of the wire, constant. H, coming to this H is also a practically constant. Almost H may change slightly, but that change can be neglected, because earlier also I told you, in both free convection and forced convection, the H value mainly depends upon the properties of the fluid, but H itself is not a property, but H is mainly depends upon those properties of the fluid, rho, mu, Cp, K. So, whether you keep insulation or don't keep insulation, the H value or more insulation or no insulation, same fluid is there. So, H value almost remains same. H may change slightly because of the change in the geometry as you are keeping more and more insulation. I am just comparing as the bare wire and after keeping the insulation, will the H value change? So, if you just ask me that a question, will the real value H really completely remains constant, means I don't say no. H may change slightly, but that variation is very small. So, we can treat that the H also as practically constant, because with the change in dimension of the geometry by keeping more and more insulation, H value may change slightly, but that can be neglected. Because H value mainly depends upon the properties of the fluid. Same fluid is existing. If you keep more insulation or no insulation, same fluid is existing. So, H value change can be neglected. You can treat it as a constant. H is also a constant. So, only variable is RO. Only variable in the function is RO. Q is a function of so many things. Only variable is RO. Why RO is variable? Because the RO value depends upon how much insulation you are putting around the wire. If you keep more insulation, RO will be more. If you keep lesser insulation, RO will be lesser. If you don't keep any insulation, RO will be RI. If you don't keep any insulation, RO will be RI. So, the value of the RO depends mainly upon how much insulation you are wrapping, you are putting around the wire. Treating all other parameters, that is Ri, L, K and H as constant. Now, Q becomes only a function of RO only. Now Q becomes a function of RO only. The value of RO depends upon how much insulation is being wrapped around the wire. How much insulation is being wrapped around the wire. So Q is a function of RO only. Okay. Now, if you want to have the maximum value of Q, we have to differentiate this Q with respect to RO and equate to 0. Mathematically, we know that as y is a function of x, if you want to know at what value of x that y will be maximum, what will do? You will differentiate that y with respect to it and equate to 0. So, similarly, here Q is a function of RO. For maximum heat transfer rate, what is the condition? dQ by dRO should be equal to the 0. For maximum heat transfer rate, what is the condition mathematically? dQ by dRO is equal to 0. Instead of this Q, we can substitute this value. Therefore, d by dRO of what is that Q? Ti minus T infinity divided by ln RO by Ri divided by 2 pi KL plus 1 upon two pi ROL is equal to 0. All other parameters are constant, only RO is variable. So, you will get that RO is equal to K by H. Please note that this K is the thermal conductivity of insulation, not the thermal conductivity of the wire. Okay. So, this K by H is called critical radius of insulation. This is called as the critical radius of insulation, K by H. Please note that this H is the convection heat transfer coefficient in contact with the wire. This H is the convection heat transfer coefficient in contact with the insulation. I mean to say this H is the convection heat transfer coefficient between the insulation and the air. Okay, that point you keep it in mind. So, what is the physical significance of this? What is the physical meaning of this formula? What is the concept of the critical radius? I would like to explain it by taking one graphical representation of the variation of Q with RO. So, I would like to explain it, very important discussion regarding the critical radius. What is the physical meaning, physical significance of the critical radius? Physical significance of critical radius of insulation. That significance you will be able to understand by seeing this graph. This is Q, this is RO. This is RO critical. This is called as the RO critical, given by K of the insulation divided by H. What is the physical meaning of this? That you can understand by taking a simple example. Suppose that I have got a wire, bare wire. I have got a bare wire. Maybe that radius may be around, say, 5 mm. I got a bare wire of radius 5 mm. And it has got some heat transfer between the wire and the ambient due to the temperature difference, because for any heat transfer phenomenon, temperature difference is a must. I have got a bare wire, maybe of radius 5 mm, example, and it is losing heat by convection to the ambient air. Then critical radius I have calculated, that is critical radius happen to be 10 mm. Bare wire radius is 5 mm, critical radius is 10 mm, that is this is 10 mm, and but the radius of the bare wire, that is without insulation, what I have considered is 5 mm, that is on the left hand side of the critical radius here. Okay, we are talking about this domain. This is the domain we are talking about. Critical radius is 10 mm, but the radius of the wire I have considered is only 5 mm. That is we are beginning the journey here. Then I have wrapped a little bit of insulation. I have wrapped a little bit of insulation around the wire. Now the radius has become 7 mm. It is losing some heat, that is some bare wire has got some Q. Then I have wrapped insulation, that means that now the radius has become 7 mm. That means you are moving this side. As compared to the bare wire, now you have got the more heat transfer rate you are observing. Heat transfer rate is increasing. Why that is increasing? That answer would be given by seeing this thermal circuit. Why it is increasing? That answer could be given by seeing this. As the RO is increasing, this conduction resistance will increase. This conduction resistance will increase. But when you look at this particular formula, this RO is in the denominator. So this convection resistance will decrease more as compared to the little increase of conduction resistance. In the left hand side domain of the graph, here, I am just giving the reason why the heat transfer rate is increasing. If you consider a wire of radius whose value is lesser than the critical radius, that means if you consider a wire whose radius is lesser than the critical radius, putting the insulation is resulting in increase of heat transfer rate. Why it is increasing? I am giving the reason here from the thermal circuit. As you are putting more and more insulation, ROE value is increasing. That would result in the little bit increase of conduction resistance, but there is a steep decrease in convection resistance. The combined effect will be, the total effect of these two will be, total resistance will decrease and heat transfer rate will increase. So that is the reason for this increase. If you begin the journey on the left hand side, any insulation wrapped around it is resulting in increase of heat transfer rate because the reason is there is a little increase in conduction resistance, steep decrease in convection resistance. The total effect will be, total resistance will decrease and this heat transfer rate will be increasing. That will continue to happen till you reach the maximum heat transfer rate. That means as you are keeping more and more insulation, heat transfer rate is also keeping increasing. But once you reach that maximum heat transfer rate, beyond that if you keep the insulation, heat transfer rate begins to fall. The reason is in the right hand side domain here. Why it is decreasing? I am giving the reason. Now the heat transfer rate will tend to increase more and this will drop little. These two arrows, these two red color arrows correspond to this one, correspond to this particular happening. So what is when this starts rising more and this drops little, what is the combined effect of these two? Heat transfer rate will decrease, because the combined effect of these two will be, red color arrows will be, total resistance will increase and heat transfer rate will decrease. So the main gist of this discussion is, after putting the insulation, whether heat transfer rate, whether it will increase or whether it will decrease, depends upon two things. What are the two things? What is the critical radius value? What is the critical radius value? And what is the radius of the wire you are considering? What is the critical radius and what is the radius of the wire you are initially considering before putting the insulation? In case if the radius of the wire initially considered is lesser than the critical radius of insulation, if you wrap the insulation around the wire, that is resulting in increase of heat transfer rate. On the other hand, if you consider a wire whose radius is already more than the critical radius, if you begin the journey here, if you wrap the insulation around the wire, that will directly result in decrease of heat transfer rate. So, whether heat transfer rate, whether it will increase after keeping the insulation or whether it will decrease after keeping the insulation, mainly depends upon whether you are beginning the journey on the left hand side of this critical graph in this domain or here. If you begin the journey here, if you keep on putting the insulation, heat transfer rate keeps on increasing, it becomes maximum. Beyond that, if you continue to keep the insulation, once again it begins to fall. If you begin the journey here, it keeps on increasing after keeping more and more insulation, reaches a maximum and then falls. If you begin the journey here, that means critical radius is 10 mm. If I consider a wire of radius 12 mm here, that means you are beginning the journey on the right hand side. Then if you wrap the insulation, heat transfer rate will decrease. So that point you have to keep it in mind, because there are two different resistances. The reason is there are two different resistances responding in a different way. On the left hand side, these yellow color arrows will hold good. On the left hand side of the graph, these two yellow color arrows will be holding good. On the right hand side of the graph here in this domain, right hand side means with reference to this particular junction. On the right hand side of the graph, these two red color arrows will hold good. Okay. There are two functions, one is logarithmic function and other is hyperbolic function. One function is increasing and another function is decreasing. The relative changes of those two, logarithmic function and hyperbolic function, will decide whether heat transfer rate will increase or heat transfer rate will decrease. That means, that is the reason why, very important point I would like to tell you, that for sufficiently thin wires, generally critical radius concept is more applicable for sufficiently thin wires. That means, for sufficiently small radius wires, for sufficiently thin wires, putting the insulation around the wire, it will result in increase of heat transfer rate. That point I would like to write here. For sufficiently thin wires, or small radius wires, putting the insulation around the wire will result in increase of heat transfer rate will result in that, I am talking about this domain, will result in increase of heat transfer rate instead of decreasing it. Instead of putting the insulation around the wire will result in increase of heat transfer rate instead of decreasing it. I said then, sufficiently thin wires. Why I am using this word is, you are beginning the journey where we are beginning the journey by considering a wire whose radius is critical radius. If we just calculate for practical values of all the insulations and practical values of H, this RO will be quite lesser, maybe 1 centimeter or 1.5 centimeter. That means you have to take a wire whose radius is 5 mm or 6 mm or 7 mm like that. That means the critical radius concept is more so applicable for sufficiently thin wires or for small radius wires. Supposing if you take a big pipe, big wire or thick wire, very thick wire, maybe 5 centimeters or 10 centimeters, this critical radius concept will not be applicable because you are beginning the journey somewhere here. That means if you are putting the insulation as you think everywhere, the heat transfer rate automatically will decrease. So what I mean to say here is, this increase of heat transfer rate after keeping the insulation is more so applicable if you consider a wire whose radius is relatively small, maybe few mm, 5 mm or 6 mm or 7 mm or maybe around 1 centimeter. If you take a big pipe and big wire, thick wire of around 5 centimeters or 10 centimeter like that, if you put the insulation around that, automatically heat transfer rate will decrease as you expect. So that is a very important thing we have to write. For sufficiently thin wires, putting the insulation around the wire will result in increase of heat transfer rate instead of decreasing it. This happens, so I am giving the reason. This happens so because as we keep more and more insulation, around the wire, there is a rapid decrease in convection thermal resistance. There is a rapid decrease in convection thermal resistance as compared to little increase of conduction thermal resistance the overall effect being decrease in total thermal resistance, the decrease in total thermal resistance and increase of heat transfer rate. So this is the main reason. Conduction resistance will increase little, but convection resistance will decrease rapidly. So that the combined effect will be total resistance will decrease and increase of heat transfer rate. Actually, this continues to happen. This continues to happen up to critical radius of insulation. This continues to happen up to critical radius of insulation, beyond which any further insulation added any further insulation added will decrease the heat transfer rate. Beyond which any further insulation added will decrease the heat transfer rate. I am talking about this domain. This continues to happen up to critical radius of insulation where the heat transfer rate will become maximum, beyond which any further insulation added will decrease the heat transfer rate. So, whether it will increase or it will decrease, it all depends upon where are you beginning the journey. You are beginning the journey on the left hand side or on the right hand side. That will decide whether heat transfer rate will increase or it will decrease. Why it is decreasing? Now exactly reverse happens. On the right hand side, why it is decreasing is conduction resistance will begin to change greatly, will begin to increase greatly. There will be a little drop in convection resistance. The combined effect will be total resistance will increase, as such heat transfer rate will decrease. So, whenever you are doing the problem of critical radius, first calculate the critical radius and then draw the graph. Put that value of critical radius, all the values, whatever they given in the problem in the graph, and then by looking at the graph, try to answer the question. I also will do that. Whenever I am doing a problem of critical radius, first I calculate the critical radius value from that formula K by H. And I will put that value in the graph, and what is the actual geometry given in the problem, I will put the graph. Whether I am on the left hand side or whether I am on the right hand side, then I will check it. Then I will try to answer the question. Okay. You also must do like that. And practical applications I will give it, and before going to that one, I am going to give the another important formula for critical radius. For sphere, for spherical body, this is a very important formula. Earlier one what I have done was a cylinder. For spherical body, for spherical shape, for spherical body or shape, critical radius of formula will be different. For spherical body or shape, or critical for the sphere will be 2K by H. Please remember 2K by H. K is the conductivity of the insulation. For the cylinder it is K by H. For the cylinder it is K by H. For the sphere it is 2K by H. Okay. So, the concept of critical radius will be applicable for the sphere also, but formula will be different, 2K by H. For the cylinder it is K by H. The practical applications of this critical radius, I will give two examples. Practical applications of critical radius. Number 1, domestic electric power cables, domestic electric power transmission cables. Domestic, the household. You must have seen that in the household, in our household electric power transmission cables from the supply to the fan or somewhere. You will be in our home, inside our house, you will see at many locations there will be electric power cables, transmission cables. You must have seen that they are all insulated. And that wire will be relatively small. They are all insulated. Why they are insulated? I am giving the reason. When the electric power is being transmitted, inside the wire, that would result in the generation of the heat. Heat will be generated. Okay, I square R. This heat generated must have to be convected quickly. Must have to be convected. This heat generated should be quickly convected. Otherwise, what will happen? This heat generated will result in the Q generated will result in the increase of temperature, and that would result in the increase of electric resistance, of the cable, because electric resistance will be more at higher. That would result in the more heat will be generated. More heat will be generated. If that is not taken off, again that will result in the more temperature rise, more electric power resistance, and most of the electric power will be wasted off. There is one vicious cycle will be developed. What I mean to say is, whenever you are transmitting the electric power, there is some heat generation. Your idea now is, we have to transmit that heat generation quickly to the ambient. I would like to give it. Otherwise, what will happen if you don't take it off quickly? That would result in because if you are not taking out, that would result in the increase of temperature of the cable. Increase in temperature of the cable. As the temperature of the cable increases, its electric resistance will increase. Again, that would result in the more generation of the heat, and that is not taken out. Again, that will increase the temperature of the cable. I want to break that cycle. For that purpose, I will keep the insulation. This insulation, after keeping the insulation, I can see that there will be more heat transfer rate. Q will be more. So that means after keeping the insulation, that heat transfer rate will increase, because the temperature of the cable, whatever I have taken, whatever the radius of the wire, after keeping the insulation, heat transfer rate will become more as compared to the bare wire, because the radius of the wire, what I consider radius of the cable, is much lesser than the critical radius. That means I am beginning the journey here. I am beginning the journey somewhere here. I am using this concept, this particular concept. Okay, that means because the radius of the cable I have selected is much lesser than the critical radius. Therefore, after putting the insulation, heat transfer rate is becoming more. So the power transmission efficiency can be increased. So by keeping insulation, heat transfer rate from cable to ambient can be increased thus temperature of cable can be kept low. Thus the temperature of the cable can be kept low. Thus its electric resistance can be kept low. Thus electric resistance can be kept low, thus transmitting more power. Thus transmitting more electric power. We all do that in our domestic cables. Otherwise, most of the electric power will be, the power transmission efficiency of the cable can be increased by putting the insulation. That means the cable radius what you are considering is much lesser than the critical radius of insulation. Okay, so finally all the domestic cables are insulated. What for they are insulated? To increase the heat transfer rate or to decrease? So to increase the heat transfer rate, they are all insulated. By increasing the heat transfer rate, you can keep the temperature of the cable low, its electric resistance low, and you can transmit more electric power through the cable. The second example is spherical electronic devices. Electronic devices, they require cooling. By putting the cable, by putting the insulation around that spherical device, electronic device may generate some heat. This electronic device may generate heat. I want to make out that heat. I want to make it more. For that, this insulation is kept. This insulation is kept to increase the heat transfer rate more, so that the electronic device temperature can be kept low. Electronic devices are temperature sensitive. If the temperature of the electronic device will increase, they cannot function well. So, the purpose of putting the insulation is to make the heat transfer more. That means, but here the formula for the already given for the spherical cases, critical radius will be R critical for the spherical shape. I had already given the formula, that is 2K by H, where K is the thermal conductivity of the insulation, not the device. So, two examples I had given. In both the examples are given, your objective, your idea is to increase the heat transfer rate. For that purpose, we have kept the insulation. So, mind that this concept of critical radius is more so applicable for the small size spheres and small size cables. In case if the radius of the wire initially considered is already more than the critical radius, definitely you will see decrease of heat transfer rate only. That note also we have to note even. Note, very important note is, in case if the radius of wire or sphere wire means cylinder, initially considered is already more than critical radius of insulation, any insulation wrapped around it will directly reduce the heat transfer rate. Any insulation wrapped around it will directly reduce the heat transfer. That because you are beginning the journey. The answer is here in the graph. You are beginning the journey here. When if you begin the journey here, automatically heat transfer rate will decrease after putting the insulation. So, whenever you are doing the problem of critical radius, please keep in mind that what is the critical radius value, what is the initial radius of the wire you are initially considering. So, that you can, I will do that problem here. I will do, yes, look at this problem. For a current carrying wire of 20 mm, this is a gate question only. For a current carrying wire of 20 mm diameter exposed to air, maximum heat dissipation occurs when the thickness of insulation is. For a current carrying wire of 20 mm diameter exposed to air, the maximum heat dissipation occurs when the thickness of insulation is. Because look at this problem, maximum heat dissipation means that will be happening corresponding to the critical radius. Maximum heat dissipation means heat loss. This is a previous gate question only. Maximum heat dissipation or heat loss would occur when the radius of insulation is critical radius. It is a cylinder, therefore K by H, critical radius, that is K by H. First let me calculate the critical radius. K of the insulation divided by H. What is the K of the insulation given? 0.5. H value is 20. Okay. H value will be 20. That is in meters. This is in meter. But I want it everything in mm. 0.5 into 20 divided into 1000. So this will get cancelled by 50. 5 into no, this becomes 25 mm. Okay. 25 mm, that is. So, but what interestingly, what he has asked is thickness. That point you have to notice. He has asked the thickness. It is not the radius. What we have calculated the radius there. So, you are getting the, what is the radius of the initial wire? Radius of the 20 mm. 20 mm diameter. That means radius will be how much? Radius will be 10 mm. 20 mm diameter means this is a wire, current carrying wire. And you have kept the insulation for maximum heat dissipation. You have to keep the insulation as how much? How much you got the answer? That is 25. We have to keep 25 mm. Then only your heat loss will be the maximum. Now we are getting the maximum heat loss. But what he has asked is the thickness, not the radius. This thickness will be, critical thickness of insulation will be how much? 25 minus 10, that is 15 mm. Answer is D. Immediately after seeing this, people may tend to go to this B answer. Wrong. Correct answer is D, because he has asked the thickness of insulation. Radius is different, thickness is different. Radius is always measured from the axis. Critical radius is measured from the axis, but he has asked the critical thickness of insulation. Okay. Look at this question. This is also regarding the critical radius, previous gate question only. It is proposed to coat, coating means painting or coating around, the putting around. It is proposed to coat a 1 mm diameter wire with enamel paint to increase the heat transfer with air. See, in all the critical radius problems, you are seeing a very small radius of the wires or the cables, very small radius, because critical radius concept is more so applicable for the small radius or the thin wires, thin cables. 1 mm diameter, right, with the heat transfer. If the air side heat transfer coefficient is 100, the optimum thickness of the enamel paint will be optimum thickness of enamel paint. That means you want to maximize, to increase the heat transfer rate. If this is the wire, solid wire, what is the radius? Quote 1 mm diameter radius, means radius will be 0.5 mm. Okay. I want to maximize. For that, I have kept the some enamel paint. Enamel coating was given. This is enamel. Conductivity of the enamel is how much? 0.1. Okay. Because you want to maximize. That is why optimum. You want to maximize because you want to increase the heat transfer rate. Look at this. You want to increase the heat transfer. That means you want to have the maximum. So for maximum heat transfer rate, obviously how much radius you have to keep? You have to keep the critical. So first let me calculate the critical radius of insulation. That is K of the insulation divided by H. What is the K of the insulation? 0.1. What is the H value he has given? 100. Maybe it is a forced convection in air. 0.1 divided by 100 meters. This is. I want to get in mm there. 1000 divided by 100. So this 10 times gets cancelled, it will become 1 mm. Critical radius is 1 mm. But what he has asked is again the optimum thickness he is asking. This critical radius we got it as the 1 mm. Radius we got as a 0.5. Therefore, this critical thickness of insulation is asking. Thickness of insulation will be 1 mm minus 0.5 mm. So answer will be 0.5 mm. Answer will be B. Correct answer is B. In both the problems I have done, they have asked the optimum thickness of. Why am I using the word optimum? Your idea is to maximize the heat transfer rate. To increase, clearly given, to increase the heat transfer rate. Because obviously we have to give the we have to look for the maximum heat transfer from the wire to the ambient. Look at this question. A stainless steel tube of 19 watt per meter Kelvin of 2 centimeter ID and 5 centimeter OD is insulated with 3 centimeters thick asbestos. If the temperature difference between innermost and outermost surfaces is 600 degrees Celsius, the heat transfer rate per unit length is. He has given a stainless tube of hollow. This is the steel. This is the steel. And it is insulated with 3 centimeter thick asbestos. This is R1, this is R2, this is R3. L is 1 meter. If no length is mentioned, we can take it as the L as length as the 1 meter. This is asbestos. This is conductivity of the steel was given. Steel conductivity is 19. Asbestos K is just 0.2. Asbestos is an insulator. Generally, asbestos roofs you must have seen. Practically, asbestos is used in making the roofs, not a RCC roof, a temporary roofs in the sheds and all. They make the asbestos because that can prevent the heat transfer. It is used in making the roofs of the small sheds, etc. And between the innermost and outermost, if this temperature is T1, junction is T2, this is T3. Between the innermost and outermost, this delta T is given as how much? 600 degrees Celsius. Between the innermost and outermost surface, the temperature difference is between the T1 minus T2, T1 minus T3. This is given as 600 degrees Celsius. First, let me keep the what is R1, what is R2 and what is R3. What is R1 based on the given data of 2 centimeter ID, radius will be 1 centimeter. R2 will be how much OD to 5 centimeters, that is half of that. What is R3? R3 is obtained by adding this thickness. What is the thickness of the asbestos? 3 centimeter thick. Thickness of the asbestos was given. So how to get the R3? To get the R3, we have to add this thickness to the R2. R2 is up to here. So how much is the thickness there? 3 centimeters. Therefore, R3 will be 2.5 plus 3, that will be 5.5 centimeters. Note that R3 will be 2.5 plus 3. So, construct the thermal circuit for this against the radial heat transfer. There will be only two resistances between T1 and T3. Between T1 here and T3, there will be two resistances. One is conduction resistance offered by the steel, and another is the conduction resistance offered by the asbestos. Please note that whenever you are drawing the thermal circuit for calculating the heat transfer rate, what terminals you are taking, what are the resistances existing between them, you have to focus on that. Now, all the gate questions like that, what are the terminals we are taking, selecting in the geometry, and what are the resistances that are existing, how many resistances and what type they are, whether it is a conduction or a convection. Here there are two resistances between, these are one terminal T1, outermost terminal is T3, because that difference only is given as 600 between T1 and T3. Between T1 and T3 there are two resistances, conduction type. This is conduction resistance offered by the steel, and this is the conduction resistance offered by the insulation. So, this is the steel conduction, this is the asbestos conduction. What is the first resistance? Ln R2 by R1 divided by 2 pi conductivity of the steel into L. L you can take it as the 1 meter, and the outer resistance will be Ln R3 by R2 divided by 2 pi conductivity of the asbestos into L. L is 1 meter. This difference is T1, T2, T3, T1 minus T3 difference given, that is 600 degrees Celsius innermost, and select substitute in the thermal circuit to get the watt per meter length, rate of heat transfer. Q will be L is 1 meter, clearly per unit length he has mentioned, clearly has mentioned L is 1 meter, that is 600 divided by Ln, what is R2? 2.5, we can keep it in centimeter, ratio only, no, R1 is 1, 2 pi, what is the conductivity of the steel? 19 into 1 plus Ln R3, R3 is 5.5 divided by 2.5 divided by 2 pi, what is the conductivity of the asbestos? 0.2, length is 1, this will be 944.72 watt per meter length, clearly as given. Answer is C. And if you just observe that thermal circuit, answer is C. First you have to get the dimensions correctly, R1, R2 and R3. Now if you just observe that thermal circuit, conductivity of the steel is 19, conductivity of the asbestos is only just 0.2. So which resistance will be relatively more? We can say asbestos. Asbestos being the insulator, it will offer a far more conduction resistance. So I can compare that. Conduction resistance of the asbestos will be far greater than the conduction resistance of the steel. That this point you can, why? Because you can look at the resistances there. This is a conductivity of the asbestos is 100 times, almost 100 times lesser than this 19. Okay, look at this value. This is far lesser than this. Therefore, this resistance will be far greater than this. Steel is a metal, very good conductor. Asbestos is a very bad conductor. Asbestos is an insulating material. I had given earlier also glass wool, asbestos, refractory brick, sawdust, wood. They are all the polyurethane foam. They are all the very good insulating materials. They can prevent the heat transfer rate by offering more and more thermal resistance. We have to should be able to compare that kind of a resistances. Like look at this. This is also a question previously asked in GATE. With an increase in the thickness of insulation around a circular pipe, there is a circular pipe, some pipe is there. With increase in thickness of insulation, we are putting some insulation. As I am keeping more and more thickness of the insulation, that is, this is the thickness, right? This is the thickness of insulation. As I am putting more and more insulation, what is happening is asking. So definitely, as we keep more and more insulation, convection area will increase. As we keep more and more insulation, convection area increases. Convection area increase. Therefore, convection thermal resistance will decrease. What is convection thermal resistance? 1 upon HA. So, as area is increasing, convection thermal resistance will decrease. As the convection thermal resistance decreases, heat loss due to convection will increase, while due to that conduction decreases. But conduction thermal resistance, what is the formula? Conduction thermal resistance ln Rho by Ri divided by 2 pi KL. So, as Rho increases, see this, as Rho increases, what will happen? Conduction resistance, that will also will increase. So, while that due to conduction decreases, but because this resistance is decreasing, the heat loss surroundings due to convection, no, here there is a happening convection. Convection heat loss due to convection increases, whereas the heat loss due to conduction decreases. Answer is A. This is the correct answer. This is the concept behind the critical radius. Thermal, see, in the critical radius concept, there are two resistances which are changing in a different way. One resistance is increasing and convection resistance is decreasing. Heat loss is asking heat loss, not the resistances. Heat loss to surroundings due to convection increases, while that due to conduction decreases. Answer is A. This is the heat transfer rate, right? As the convection area is increasing, as we are putting more and more insulation, convection area keep on increasing. When there is a more convection area, as the convection area increases, this resistance decreases, convection resistance. So, the heat transfer by convection will increase. That is the answer A. While that due to conduction decreases, because the conduction resistance is increasing. This is the conduction resistance. This is the convection resistance. A long glass cylinder of inner diameter and outer diameter carries hot fluid inside. If the thermal conductivity of the glass is, it is a glass cylinder. This is R1, this is R2. Some hot fluid is flowing inside, carrying hot fluid. Conductivity of the glass is given 1.05. What is the conduction thermal resistance of the glass is asking. Formula will be ln R2 by R1 divided by 2 pi KL per unit length. L you may take it as the 1 meter. R1, R2 you can substitute. Outer diameter, what is R1? R1 is, you can take d2 by d1 is, R2 by R1 is d2 by d1. You can directly take the diameter ratios. You will get one of those answers in Kelvin per watt. conduction thermal resistance of the glass. Heat transfer through a composite wall is shown in the figure. Both that sections have equal thicknesses. It is a previous gate question. This is L, this is also L. Conductivity of the one section is K and the other section is 2K. It is a simple conduction composite slab. Conduction heat transfer through a composite slab. The interface temperature is asking this junction temperature is asking. This junction temperature, right, Ti. So, if you just draw the thermal circuit, this is the heat flow, this is the Q value, this is K, this is 2K. So, draw the thermal circuit, you will get the answer. How many resistances? Between 600 and 300, only 2 resistances. This is 600 Kelvin. Take care of the units there. Take care of, sometimes you will give Celsius, sometimes you give answers will be asked in Celsius, Kelvin. You have to be very extra careful. This is Ti. What is this resistance? L divided by Ka. This is L divided by 2K into A. Flowing current is Q. Just write the thermal circuit, that is Q is equal to 600 minus Ti divided by L by Ka, that is equal to Ti minus 300 divided by L by 2K into A. Most of them will get cancelled there. You will get the formula for answer for Ti in Kelvin. Current is same, right? Current is same. So, we have taken the this particular potential drops. Current is same throughout series circuit. You will get the answer. I think answer will be 400 K. Answer will be 400 Kelvin for this question. So, composite wall questions are very, this is the previous gate questions. But whenever you are drawing the thermal circuit, remember that thermal circuit is always drawn between two terminals, okay, two temperatures, right. So, where are the temperatures? What are the temperatures we are considering? Where are the temperatures? And what are the resistances existing between them? That should be very, very careful. We cannot simply take the thermal circuit for granted. When you select the temperature profiles for the thermal circuit, how many resistances are existing between the terminals and what are the types of those resistances, whether it is a conduction or a convection or both are there. We have to tell. Here between 600 and 300, only 2 resistances are there, both are conduction resistance. Sometimes there may be fluid given here, that temperature is given, that then the convection may come into picture. So, what are the terminals and how many resistances are there and what are those types of resistance? Type means whether it is a conduction or a convection. That we have to have a very clear idea in drawing the thermal circuit. Then only we can get the correct answer.